Welcome back. Today we're going to begin Chapter 3, Differentiation Rules. A differentiation rule is a formula to calculate the derivative function for given function. Depending upon what kind of function is given, we'll have to deal with different types of formula. We'll have to deal with polynomial and exponential functions, a product or quotient of two or more known functions, trigonometric functions, composite functions, and many more actually. So this is going to be a rather long chapter, so I broke it down into several smaller notebooks. And here's one. The first one deals with elementary differentiation, and I'm going to concentrate upon power functions, exponential functions, and a little bit of logarithmic functions. Let's review what is a derivative first. We're going to review as quickly as possible. So I hope everybody remembers these pictures. Slope of secant line, this green line, can be expressed as delta y over delta x, rise over 1, difference of y coordinate over difference of x coordinate. When the second reference point gets closer and closer to the first one, or delta x and delta y go down to 0 or infinitesimal, then those green lines converge to this red line, the secant line converging to the tangent line, and we can even animate it kind of like this. Okay, that was fun. All these point toward the limit notation. Here's the limit notation. The green secant line slope can be calculated as f of b minus f of a. F of b minus f of a over b minus a, this quantity here, the difference of y coordinate over difference of x coordinate. And upon taking the limit, we have the slope of tangent line, the red line. That's a derivative. Or you can express it as delta y over delta x, and then as infinitesimal over infinitesimal, dy over dx. That's the equivalent. Or you can express b as a plus h, and re-express the same limit as follows. They're all the same. And the last one is most popular. And we use that last notation to define the derivative function, even though all three notations are equivalent. So here it is. Derivative function is given by a function where all those x values give us the slope of tangent line of the first function. So we end up with different function, and there must be some relation between the first function, original function, and the derivative function. That's what we're looking for here. We're not going to prove anything here, in this notebook at least, so let me just take a shortcut. Here is the constant rule, addition rule, coefficient rule, or which I often call trivial rules. The derivative, this is derivative notation by the way, the derivative of constant is always 0. You can see this kind of behavior in any kind of plot. For example, here's a constant function. As you can see, the slope is 0. Rise over 1 is the slope, but rise is 0, so we have 0, and not coincidentally, the derivative function is constantly 0 for a constant function. Now, the other rules are a little bit harder to see, but they fit our common sense very well. Derivative of sum is sum of the derivatives. If you have coefficient, you can multiply coefficient later. But these rules, these trivial rules by themselves are not very helpful, so we need some further formulae. And here's one, the power rule. How do you find out the derivative of a power function? Well, n to the x to the nth power becomes n, x to the n minus first power. So power comes out as coefficient and subtract 1 from the power. How do we actually work it out? Let's go through that with a couple of examples. So the first example, f of x is given like that. Let's find out the derivative. Now here in the second rule, you can see that you can take the derivatives of each term and then add them up later. So if we have more than 2, then repeat this rule, and then you're going to have just sum of the derivatives. So we'll find out the derivative of this term, and the third term, and the fourth term separately, and then add them up. What's the derivative of x cubed? Applying this power rule straight ahead, we have 3x squared. Okay, how about the derivative of the second one? Oh, by the way, this derivative happened to be the same as that one. That was coefficient. That was just coincidence though. Okay, let's move on to the second one. What's the derivative of this part? If this 3 hadn't been there, the derivative of x squared will follow this power rule. So we'll have just 2x to the first power, or simplifying just 2x. However, there was 3. 3 was right here. So you have to multiply 3 afterwards. So this is 3 times 2. So in the end, you're going to get 6x. You can do the same thing for the third term here. What is the derivative of 4x? 4 times the derivative of x. But then again, what is the derivative of x? Oh, that's interesting. This is just first power. So if I multiply 1 and then I'm going to get just 4 times 1, subtracting 1 from the power, I'm going to get 0 power. What is 0 power? 0 power is defined as 1. So this is 4 times 1. But of course, times 1 doesn't change anything. So just 4. Finally, the derivative of the square root part, don't panic. This is just a constant. No matter how complicated it is, derivative of constant is 0. So we have minus 0. But minus 0 doesn't change anything. So the final answer should be just that. Is that right? Let's check the answer. Oh yes, that's right. Okay. Let's go over to the next problem. This is going to be slightly more challenging because we have a bunch of radicals here. Can we still use this power rule? Oh yes, you can, because those radicals are power functions. So what is the first term? 3 square root of x. It can be written as 3x to the certain power. What is it? 1/2 power. Next. 4 is coefficient, x to the which power? We have square root, so it should be 1/2 power, but that's in the denominator. So negative 1/2 power. 2 is coefficient, x to the which power now? X to the first power times x to the 1/2 power. So we have 3/2 power. That is a simplification or conversion of this one. This is in traditional radical form, but this one is in power form. But these are the same, not the derivative yet. How do you find out the derivative? Well, we'll have to apply that power rule and then all those rules over here, trivial rules. Let's put those together. 1/2 is 1/2 is the power, so that's gonna be multiplied to this coefficient. So 1/2 times 3, I'm getting 3/2. And subtracting 1 from the power, negative 1/2 power, 1/2 minus 1. How about the next one? Plus 4 was there, x to the, but negative 1/2 power, that's going to come out, and I'm going to multiply this negative 1/2 and 4 here. So negative 1/2 times 4, I'm getting negative 2. How about the power? I have to subtract 1 from the power. So negative 3/2 power. How about the next one? 3/2 times the coefficient negative 2. So I'm getting just negative 3. X to the what power? Subtract 1 from the power. 3/2 minus 1. I'm getting 1/2 power. So the first line is just power form conversion. It's not a derivative computation. I didn't use any of these rules. Applying all these rules, all those terms, this derivative rules simultaneously at a single step, we got the derivative. Is that the answer key? Well, I hit it. Let's find out. We'll open up the cell. Yes, the computation we just did is correct. There goes the derivative of the power functions combined with some trivial rules.